In this video series, I'm going to teach you all of the A-level physics with just a board and a pen and my voice. No cameras, no fancy tech, just me writing on the board. Let's start with matter and radiation. And the first topic we're going to have a look at is called inside the atom. Now, while I'm teaching, while I'm talking, I'm going to be writing, which is going to force me to slow down. That is deliberate. It means that you've got time to make your own notes. It also means you've got time to digest what I'm saying. And if you've got any questions, you can go in the comments and ask them. And if I don't get a chance to answer, someone else who's very knowledgeable will be very happy to answer or correct any mistakes I make or anything like that. So let's start by considering the structure of the atom. And I think that most people are going to remember the structure of the atom from GCSE level. The structure of the atom is a nucleus, which is positively charged, circled by electrons, which each have a negative charge. And they sit some distance away from the nucleus. So let's just draw a couple of electrons in here. And I'll draw them as little blobs like this, because why not? Now, if you've studied GCSE chemistry, you might be a bit disturbed by this little sketch and be saying, well, hang on a minute, sir. You've got two electrons and one particle in the middle. And I suppose, yes, I do have one particle in the middle, because I could describe the nucleus as a particle. But the nucleus is not a fundamental particle. It contains other particles. So this is the nucleus, and we have electrons around the outside. Now, this is not to scale, not even close to being to scale. The nucleus itself is actually significantly smaller than this. The nucleus itself is about 1 in 10,000 times the size, so 1/10,000th the size of the atom. It's a very small composite particle, the nucleus, just like that. So the majority of the atom is empty space. Empty space. And we can talk about Rutherford's experiment a little bit later if we want to. So that's a very coarse structure, the nuclear atom. It has a nucleus. But what's inside the nucleus? Well, inside the nucleus, there are other particles. There are protons and there are neutrons. So if I wanted to zoom in on the nucleus and have a look what's inside there, then what would I see? I would see maybe 2, 3, 4, 5, 6. Let's have 6 protons, because why not? And let's have 2, 3, 4, 5, 6 neutrons, just like that. And the protons themselves have the positive electric charge, so let's label them with the plus. And the neutrons are neutral particles, and that's what we find inside the nucleus. These protons and these neutrons. Now, collectively, we call protons and neutrons nucleons. That's what we call both of those. So let's just draw a box around them and say that those are called nucleons. Let's spell it right. Nucleons. So nucleons are protons or neutrons. And we need to know that sort of terminology. So nucleons are found in the nucleus. Electrons are not found in the nucleus. They are orbiting the nucleus in what we could call orbitals, or we could call them shells, or I suppose we could even call them energy levels, but we'll come to that later. So let's draw a quick table of the properties of these different particles then. We've got our protons, we've got our neutrons, both of which are found in the nucleus, and we've got our electrons. And they are what make up our atom. So let's just draw that. Let's draw up a nice table. One of the things we can look at, one of the properties we can look at is called charge. Oops, let's get the straight line tool off. It's called charge, electric charge. And we could measure that charge in a unit called coulombs. Now, why do we put the units after the slash? The answers to that will come a bit later, but effectively we're dividing the quantity called charge with the unit called coulomb because the quantity called charge already contains the unit called coulomb. That way I can just write a number. So protons have a charge of 1.602 times 10 to the negative 19 coulombs. Neutrons have no charge at all. But the electrons have a charge of negative 1.60 times 10 to the negative 19 coulombs. And this is actually one of the big mysteries of physics in A-level, is why do electrons and protons happen to have the same charge? It's not actually an easy thing to answer. We could actually look at the mass of the particles as well. Oops, did it again. The mass of the particles, and we could measure that in a unit, let's call it kilograms. So the proton's mass, absolutely tiny, about 1.67 times 10 to the negative 27 kilograms. The neutrons are a touch more massive, but you wouldn't notice it to 3 significant figures, but they are a little bit more massive. The electrons, on the other hand, much, much, much less massive, orders of magnitude less massive. They are a very, very low mass particle. Okay, well, let's add some more columns here, because we don't usually learn, when we learn about the particles at GCSE level, we don't usually learn about their charges in coulombs. We usually learn about them as a relative charge. So let's write this as relative charge, and it's relative to the proton. This would be 1, 0, negative 1. That's still true, and it's still useful to know, because when we are trying to work out the charge of these particles, we look at the data sheet and we'll find the charge of the electron is written, but not the charge of the proton. So we'd have to know that the charge of the proton is the same magnitude as the charge of the electron. And relative mass, this is relative to the proton, so that's 1. Neutrons are a tiny bit more than 1. A tiny bit more than 1. And the electron is sort of 1/2000th, or 0.0005, something like that. 2,000 times the 2,000 times less than the mass of the proton, roughly. More like 1,800 and something, but that's close enough. So there's our table telling us all about the particles inside the atom, which are broken into nucleons, that is protons and neutrons, and electrons. Now, when we want to write down what is inside an atom, we can use what's called nuclide notation. Nuclide notation. Lots of words are very similar here, not nuclide, nuclide. Nucleus, nucleon, nuclide. Neutron. There's loads of particles, loads of words that sound very similar. We just have to get used to that. So nuclide notation you've probably already met. So let's give some examples. Let's go with oxygen. And you might have met oxygen written like this and perhaps like this. And we can break down what the different parts mean. So the bit down here is got some names. It's either called the atomic number, that's what I prefer to call it. Sometimes it's called the proton number. But it is the number of protons found in the nucleus of that atom. We also have this number up here, which is called the atomic mass, also sometimes called the mass number or called the nucleon number. And that's becoming more popular. It is the number of nucleons, that is to say, protons and neutrons found in the nucleus. So what about this other little symbol up there on the right? Well, that symbol there is the charge of the particle. In this case, it's an ion of oxygen. So let's say charge of the ion. Or I'll just say particle. Atoms are particles, ions are particles, electrons are particles, protons are particles. Just like that. And then we have our chemical symbol here. So there is some redundancy of information here because the chemical symbol tells you what the element is, and that's also determined by the atomic number. So there is some redundancy of information here. But there we go. That is the standard nuclide notation. In general, we can use X, just like that. We can use a Z, just like that. And we can use an A, just like that, in general. And so X is our chemical symbol, Z is our number of protons, and A is our number of nucleons. So remember that A is not the number of neutrons. A is equal to Z plus the number of neutrons. Okay, that's something that you need to know. Let's just delete. I deleted too much. Let's just delete them and make the equal sign in black because it bugs me otherwise. There we go. That is what A is equal to. Okay, fine. So that's nuclide notation. Why is that useful? Well, because there are some situations where you might have two particles, maybe they're atoms, maybe they're ions, that are exactly the same element. Let's just compare these two carbons, but they have different number of nucleons in their nuclei. Just like that. Let's move this one a little bit closer because it's bugging me. So you might end up with something like this. Now, those are two different isotopes of the same element. And in both cases, we have 6 protons. In both cases. And because we have 6 protons in the nucleus of these atoms or ions, not clear, there's no charge symbol, so these are atoms. And because they've got the same number of protons, they are the same element. That's how you know. But they have different numbers of neutrons. So they have 12 subtract 6 neutrons, or 14 subtract 6, 8 neutrons. So they are what we call different isotopes. It means that they have different numbers of neutrons in their nuclei. So we could say that 2 different isotopes of the same element, and this is important. I don't like saying an isotope has the same number of protons, because a single isotope has the same number of protons as what? That doesn't make any sense. They're all isotopes. Carbon-12 is an isotope. Carbon-14 is an isotope. Oxygen-16 is an isotope. They're all isotopes. But the important thing is 2 different isotopes of the same element. Now, they have the same number of protons. Let's write that a bit neater. Same number of protons in each nucleus, but different numbers of neutrons. That's what makes them isotopes. So what I will say is that they react chemically in exactly the same way. That's why they're the same element. Same number of protons means same number of electrons. And I could even label the number of electrons. Because there's no charge symbol, this must have 6 electrons. And this must have 6 electrons. There's no charge symbol, which means that the number of protons and number of electrons must be the same because it's a neutral particle. It's an atom. So two different isotopes of the same element of the same number of protons in each nucleus, but different numbers of neutrons. So they will chemically react the same way. They're the same element, same place on the periodic table. But they do actually have different masses, which leads us on to a new quantity called specific charge. Now, specific charge is useful, especially later on. At the moment, you're going to wonder, why are we bothering with it? But go with it. Specific charge is going to appear again later in your A-level course. Specific charge, and we don't have a nice symbol for this at A-level. I'm sorry, we just don't. Is the charge of a particle, and that could be any particle you like, ion or electron, proton, or even more exotic particles that you're going to learn about in this course, divided by the mass of the particle. So an atom has a specific charge of 0 because an atom has a charge of 0. But ions have a non-zero specific charge. Electrons have a non-zero specific charge. Protons have a non-zero specific charge. Neutrons, their specific charge is 0. So it's going to be quite important to be able to calculate that later on. And we'd usually give our answer in coulombs per kilogram, but it doesn't have to be. You could use any unit of charge you like. This is usually measured in coulombs, the usual unit of charge that is used all the time in even GCSE physics, and this is usually measured in kilograms, just like that. And that's it. We don't have to say anything else about specific charge at this point, just to be able to measure it. And so concludes the first lesson on matter and radiation. Hopefully you found that useful.